So before studying that complex number, let us understand why we get the need of complex number. Earlier we have the real numbers. So why we are studying the complex number? So when mathematicians faced these type of equations, let's say x square plus 1 equals to 0. And to get a solution of these type of equations, what we need to do is x square is equals to minus 1. That means x square can't be equals to minus 1 in case if x is a real number. But if in case x is a complex number, or you can say an imaginary number, we can say that x will be equals to plus minus under the root minus 1. And then mathematicians defined this number root under minus 1 as iota. So we can say that x will be equals to plus minus iota is the solution to this equation, where I is what we call it as iota. Okay. Now let us understand what iota deals, or how we can deal with iota, or what we call it as algebra of iota. Okay, let us understand some basic properties of iota. The first one is, let's say if we have iota, that is root under minus 1, and second iota square, it will be minus 1. Now if I talk about iota cube, then this I can write this as iota square into iota, hence that will be iota square, as we already know this is minus 1, minus 1 into iota, this is minus iota. Okay, and if iota power 4, this we can write down using iota square into iota square, hence this is minus 1 into minus 1, that will be equals to plus 1. So if we move further like this, iota power 5, so this will be iota power 4 into iota. Hence we can write this as iota because iota power 4 is now 1. So that means now going forwards we will follow this cycle. Iota power 1 is iota, iota power 2 is minus 1, iota cube is minus iota, iota power 4 is plus 1. And similarly, if I need to find out, let's say iota power 98, so that will be equals to, what we need to check is, if I divide this number with 4, what should be the remainder? Okay, so if I divide the number 98 by 4, I can write this as iota power 4 into 24. That will be iota power 96 into iota square. Hence we know that iota power 4 is equals to 1. So that means it is 1 into iota square. Hence this will be equals to minus 1. So we can simply say that iota power 98 will be equals to minus 1. Okay, this is a very important concept. Like what we need to check is the cyclicity of 4. Means we need to check whatever the power of iota is given to us, we need to just divide it by 4 and get the remainder. And whatever is the remainder, like 1, 2, 3 or 0, so we need to correspondingly put the value of that number. Let's say if I need to find out iota power 999, that is, I can write this as, if I divide the number by 4, I will get the remainder as 3, because I know that 1000 is exactly divisible by 4. So this is 1 less than 1000, hence the remainder will be 3 in this case. So simply I can write this as iota cube, and hence this will be equals to minus iota. So this is what we call it as algebra of iota. Now let us talk about what is a complex number. Now we have studied why we get the need of complex number. Now we will talk about what is a complex number. Okay, so we can write this as any number which can be expressed, any number which can be expressed in the form of a plus iota times b, where iota is what we already know, this is root under minus 1, and here a and b belongs to real number. So any number which can be expressed in the form of a plus iota b is called a complex number. So let us see how to plot a complex number in an argand plane. Argand plane is that plane where we plot the complex numbers. But in case of real numbers or the numbers that we have deal till yet, so these were Cartesian planes, or what we call it as rectangular coordinate system. Okay, so here the horizontal line is what we call it as real axis, and the imaginary line is what we call it as imaginary axis. This is vertical line. Okay, this is what we call it as imaginary axis. Okay, if I need to plot any point in the Argand plane, let's suppose if we have the complex number denoted by z is 2 plus 3 iota. So here we need to note that this 2 is the real part of the complex number, and here 3 is what we call it as imaginary part of the complex number. So in the complex number z is equals to a plus iota times b, I can say that a is a real part of z and b is a imaginary part of z. Okay, so if a is a real part of z, that means if we need to plot z is equals to 2 plus 3 iota, we need to move two distance on real axis. That is, let's say this is 1, this is 2. I am traveling two distance on the real axis, and if I need to travel 3 units here, that will be 1, 2, and 3. This is 2 comma 3, or I can directly write this as 2 plus 3 iota is equals to z here. So this is the point z is equals to 2 plus 3 iota in the Argand plane. Now this is how we can plot this point, and if I join this point with the origin, so the distance that this point travel, that means OA, the distance OA is what we call it as mod of z or modulus of the complex number, modulus z. Okay, that means the mode value of this complex number, and to get this mode value, let us use the Pythagoras theorem. In the horizontal we have traveled 2 distance, in the vertical side we have traveled 3 distance. So this distance we can find it using Pythagoras theorem. Hence this will be 2 square plus 3 square, that will be root under 13. Okay, so that means the mod z of any complex number where z is equals to, let's say, a plus iota times b, that will be equals to root under a square plus b square. Okay, this is a little information about the modulus of a complex number. Now let us talk about what is the argument, or let's say the conjugate of a complex number. So first we will talk about the conjugate of a complex number. So right now I'm covering the topics in very brief sense. Okay, so whenever we will discuss the chapter in detail, we will cover all the topics in detail. Okay, so now I'm talking about z is equals to, let's say, a plus iota b is a complex number given to us, and if we need to find out the conjugate of this complex number, that is, the conjugate of any complex number is denoted by z bar. This is a sign of bar over the complex number z, and that is equals to a minus iota b. You just need to change the sign of the imaginary part. Now let us see the physical significance of conjugate of a complex number. Okay, let me draw the point z on the Argand plane. This is my real axis, this is imaginary axis. Let's say if we have any point z equals to a plus iota b on the Argand plane, that means this distance is a and this distance is b. And if I take the conjugate of this complex number, then it will be the mirror image of the complex number in the real axis. That means if I try to find out the mirror image of this complex number z in the real axis, that point will get inverted here, and this is your z bar, that is equals to a minus iota b. And if I join this point with origin, I will get mod of z bar. Okay, here you can see that this distance on the real axis is again the same a, and this distance now becomes equals to minus b, because now you're traveling to below side. That is the same distance b above the y-axis, and this is the same distance b below the and this real axis. Okay, so that means only the sign of the imaginary part gets changed when we take the conjugate of a complex number. Now let us talk about some properties of conjugate. So talking about the properties of the conjugate, let's suppose if we have the two complex number in addition, that is z1 plus z2, and I need to take the conjugate of both, then that will be equals to z1 bar plus z2 bar. Okay. And second, if I need to take the difference of the two complex number and then I need to take the conjugate of that, that will be further equals to z1 bar minus z2 bar. And same will be z1 into z2 bar whole bar, that will be equals to z1 bar into z2 bar. Okay, and the same will apply to z1 by z2 bar whole bar, that will be equals to z1 bar upon z2 bar. Okay, so these are the some of the basic properties of conjugate of a complex number. Now let us talk about argument of a complex number. So talking about argument of a complex number, let's say this is my real axis, real part of z, and here we have imaginary axis. And let's say if the complex number, we will consider the case 1 when the complex number is in the first quadrant. So when the complex number is in the first quadrant, z is equals to a plus iota b. That means a and b both are positive here. A positive, b positive. That means the complex number is in first quadrant. Okay, so when we have the complex number in the first quadrant and talking about the argument of a complex number, in this case, argument is the angle that the complex number on joining with origin makes with the positive direction of real axis. So this angle phi in this case is called as the argument of this complex number z. Now to find out this angle phi, what we can use is using trigonometry. Okay, that is this distance is b, this distance is a. So I can use trigonometry and tan phi will be equals to b by a, and hence phi will be equals to tan inverse b by a. So this is the argument when the complex number is in the first quadrant. And kindly note that the argument theta or phi will always lie between minus pi to pi. This is the principal argument lies in minus pi to pi. Now let us consider the case 2 when we have the complex number in the second quadrant. Complex number in second quadrant. Okay, so when we have the complex number in the second quadrant, that means now here real part will be negative but imaginary part will be positive. So here is real part and here is imaginary part. Now we can say that the complex number is here, that is z is equals to a plus iota b. Here a is negative, b is positive when we have the complex number in the second quadrant. So what we can do to find out the argument, so the argument in this case will be this angle theta, but to find out this angle theta we should first find out this angle phi. Okay, so this will be the distance now a and this will be your b. We already know that a is negative because it is in the left hand side of the imaginary axis, or we are going left to the origin. Okay, that means tan of phi, if I apply the modular sign here to avoid the confusion of whether a or b are positive or not, so that will be equals to b by a. We already know that a is negative, but the negative sign will be compensated by this modular sign. Okay, now theta plus phi is equals to pi. That means theta will be equals to pi minus phi, and hence this is equals to pi minus tan inverse b by a. Okay, so this is the argument of the complex number z is equals to a plus iota b when the complex number is in second quadrant. Now let us talk about the third case when the complex number is in the third quadrant. So argument of complex number when complex number is in third case, third quadrant. So when we have the complex number in the third quadrant, that means both, if z is equals to a plus iota b, here both a and b are negative. So a and b are both negative. That means this is our real axis, this is our imaginary axis. So the complex number will lie somewhat here. Let's say this is equals to z is equals to a plus iota b. Now we always measure the angle with respect to the positive direction of real axis. That means now in this case we need to measure this angle. This will be your theta. Okay, to measure this angle first we need to find out this phi. So this phi will be now equals to tan of phi. Both b and a are negative. This is a, b, this is a. Hence this will be equals to, no need to apply the modular sign here because we already know that both a and b will be negative. And hence this is equals to b by a is tan of phi. Okay, so here phi plus theta or theta plus phi is equals to minus pi, and hence theta will be equals to minus pi minus tan inverse b by a. Okay, so this is the argument of the complex number when the complex number is in third quadrant. Now quickly see the argument of the complex number when it is in fourth quadrant. Complex number in fourth quadrant. So this is real axis and this is the imaginary axis. And let's say right now we are in the fourth quadrant. So in fourth quadrant, A is positive and B will be negative. Okay, so this distance is A, this is B, and this angle phi will be your this argument in this case. Okay, so we know that tan phi will be equals to now minus b by a because b is already negative. So phi will be equals to minus tan inverse b by a. Okay, I am taking this as modulus here because the phi we are measuring it anti-clockwise, so this should be negative in this case. Okay, so I can conclude that the argument of the complex number in all the four cases that we have find out is very important from exam point of view. Okay, and we have a lot more many things to discuss in this complex number that we can see in our regular lectures. Okay, so I hope you have enjoyed the lecture. Thank you.